Last thing I want to go over for the test review is RC circuits, whether they're charging or discharging. So the first thing you need to do is know what the graphs look like for charging and discharging capacitors. So this is talking about what do these equations look like. So you don't have to memorize the equations, they're right here, but you should know that anytime the equation looks like this, where it has the 1 minus e, then the graph is going to, let me just minimize this here, the graph is going to look like this. Whether this is Q or this is V, doesn't matter. This is going to be time. The graph looks like this. But for any of the other graphs that have the e to the negative t over tau, all three of these graphs look the same, and those are going to look like this. So it doesn't matter what the variable is here on the y-axis, this is time. The graph looks like this for e to negative t over tau. But for 1 minus e, it looks like that. So what this means is that if I tell you, okay, you're looking at the charge on a capacitor that's charging, then the graph looks like this. And how do you know if it's charging or discharging if I don't tell you if it's charging or discharging? It depends what it's going to be connected to. So if it's charging, that means that the capacitor is initially uncharged, and there would be a capacitor, there would be a battery, a resistor, and a capacitor. And you'd be told that this capacitor is initially uncharged, and then at some moment the switch is closed here, and then it starts charging. And then you know it looks like this, because there's the battery charging it. If it's a discharging capacitor, then the circuit is going to be in such a way that your capacitor just has the resistor there, there's no battery. The capacitor has to start out being charged in order for it to be able to discharge through that capacitor, and then any of the graphs for Q, I, or V would look like this. So conceptually you want to understand what happens, especially for charging capacitors, what I'm going to cover, but you want to know what happens for the discharging one as well. So for the charging capacitor, which is this one over here, I'm just going to draw it a little bit bigger here. So you have just closed the switch, so that means that the capacitor has not been charged yet. So there's no charge on the capacitor. And if there's no charge on the capacitor, then there's no potential difference across the capacitor. Because if you remember the equation that the capacitance is the charge per delta V, then that means that the delta V would be equal to the charge per capacitance. If there's no charge, there's no voltage. So if you have a voltage here, then that means that if this one is 0, then that means that at the beginning, delta V is all on the resistor. It gets the full potential difference. So if there's the maximum potential difference, then that means that there's going to be the maximum current through the circuit, because the current through the resistor is given by delta V over R. So having the maximum potential difference across the resistor means the maximum current that's going to go through that whole circuit. And so the next thing is, if you want to find that maximum current that happens as soon as the switch is closed, then you would just use that delta V over R. It's called V naught here, but it's the same as delta V. And then what happens after the switch has been closed for a long time? So now the capacitor has had time to charge. So it's going to charge until it has its maximum charge. To find that maximum charge, you could use this equation right here, which is going to be C times V naught, where V naught is again equal to delta V, because this time the capacitor is getting the full potential difference, delta V. So you can just think of it as this gets charged up here, and this is negative, and the charges are going to keep flowing until this delta V is the same as this one. And then charges will stop flowing, because then you'll have these wires will be equipotentials and charges are not going to flow. So we've got max charge on capacitor, max potential difference, and that means that we cannot have any potential difference across the resistor because the capacitor already has it all. And so if you're trying to find a current through the resistor using V over R, there's no potential difference, there's no current. So no current flowing here. So you can think of it, as I just mentioned, that since this is full with charge, these two wires here are the same potential. Charge doesn't flow. Charge only flows when there's a potential difference. So if you are being asked something about what happens as soon as the switch is closed, or after it has been closed for a long time, then you can use these kind of shortcut equations to figure out what's the current or what's the charge. But if you're asked for anything at some time in between when the capacitor is not fully charged, then you'd have to use one of these equations. Now, if you're dealing with a discharging circuit, which would be one of these, then you have to use one of these equations to find the charge, current, or voltage at any time. Also, remember that the tau in all of these equations, and this is getting to the last bullet here, find a charge, current, or voltage on a resistor or capacitor after a certain time. So all of these equations are giving you everything that you want to know about the capacitor. Alright, so if you're asked for something about the resistor, it would be one of these shortcut things like, okay, after it's been closed for a long time, what's the current through the resistor? And you say 0, you don't have to use an equation. So if you're asked about a capacitor, charge, current, or voltage at any time other than the beginning or the long time, use one of these, and don't forget that tau equals RC. So hopefully you're given R and C so you can find tau and plug in whatever time that you need. And the last thing I want to mention is another shortcut I mentioned in class. So if you calculate RC and let's say it's equal to 0.05 seconds, and then you're asked, okay, what's the current through the circuit when time equals 20 seconds? What is the current? Well, and let's say it's a charging capacitor, right? So instead of plugging 20 in for time, 0.05 in for tau here, then all you need to do is say, okay, well, this time here is much, much greater than the time constant. So that means that this is a long time. So the current is just going to be 0. So no use wasting time trying to find a max current that you can plug in here to then plug in all those numbers and get something like 0.00001 amps, which is basically 0. So make sure to use these to really help you conceptualize what's going on so that you don't take up too much time using equations if you don't need to.